My name is Abhijit Roy. I'm a software maintenance engineer at Red Hat Products AI team. Hi, Anindita.
Hi everyone, I'm Anindita. I work as a data scientist at Red Hat and former researcher at Tata Research. Thank you.
Today's focus will be on energy efficient LLM serving. We'll be focusing on this topic. The reason because there is too much of we are trying to adopt LLM everywhere, but we are not that much focusing on the energy emission part. And we'll try to focus like what drives energy, especially when we are using any kind of AI stuff. So in first part of our talk we will try to see from where the energy consumption comes from and how we can use efficient LLM inferencing technique, what are the available options in market, and also we will try to see a demo how to run same model on a comparatively low hardware. And in second part of our talk we'll try to correlate this with green AI. What is green AI? What we can do to achieve better energy consumption. Okay, so what drives energy demand in AI? So we have mainly two parts called model training and inference. And as you everyone most aware, right? Whatever we do, it's heavy compute kind of stuff. So we need data center for storage, for GPU, and for networking for so many things. So there are when it comes to LLM, there are two main components. One is first building the model or training the model. But model training is something which we will be doing once, right? We'll not like do the training every day. So what we will doing every day 24 by 7 into 365. So we use chat gpt, right? So like regularly we are hitting chat gpt, we are using perplexity. So when we are interactive with the model, we are doing the inferencing. So inferencing is something that go 24 by 7. So we need to focus on that part so that we can reduce the energy consumption on the part which is running 24 by 7. Okay. So a recent study from Nvidia shows like 60 to 90% of LLM emission is come from inference. And one more thing I want you to focus like when from a like individual perspective, if you are using chat gpt or perplexity or anything, you are just using it maybe like not all the time, but when you are scaling up, when you are using it in production or in your company, it will be like round the clock things. So inference at scale, billions of parameters, and one parameter equal to gpu compute, storage, networking, so many stuff, and all these are high energy uh, consuming thing. So in our previous slide, we have tried like we will be focusing on optimizing inference, but how we can optimize the inference. So there are two types. Either we can stop using the large model, we can focus on the slm, but slm using slm comes with some kind of trade off, right? Slm cannot do everything, and at the same time slm are very much task specific, and mostly we use a general purpose model until unless I have any kind of special use case. So I am left with one more option, is like I need to use the resources efficiently, especially the gpu. So what are the available options we have? There are a lot of options. Like when it comes to like using on your own laptop, olama is the best one. Like it's lightweight. Using olama you can simply run any large language model, the quantized version of the model. And for enterprise you can use tensorrt from nvidia or vLLM. So in our today's talk we'll be more focused on the vLLM part. So why vLLM? So because we have seen a significant like it try to cut down the energy or try to improve the throughput in several ways. So the moment UC Berkeley research team started working on it, VLLM, it started getting the attention from the part when it has shown like VLLM is capable of utilizing memory far better, especially compared to Hugging Face transformer. And at the same time, like as day passes, like vLLM is evolving, like it also allows you to do speculative decoding, where we will be using draft model and LLM. So for smaller task or for initial purpose, we will use the small model to generate the token, and we will use the LLM as a validator or validation purpose. And it also use like it allow you to use tensor and pipeline parallelism. What it does, so say for example, in my system I have 4 GPU. So right now I am using a small model which don't need 4 GPU. I need only 1 GPU. So I can easily tweak that how many GPU I want to use, and there are so many other parameters also. It also allows you to pipeline parallelism, like some models like DeepSeek and are all. It's not like allow you to run on single node where you need multiple node. Then it gives you that mechanism to do the pipeline parallelism, and it also supports quantized model. You can quantize your model and you can use it in VLLM. So, before jumping into the how VLLM optimize the memory, efficient memory uses, or how efficiently VLLM use the memory, that means GPU. Let's first little bit get background of the what KV cache is. KV cache is a general optimization technique used by LLM to like fasten off the token generation process. So in LLM, we have mostly like key and value, and we have those attention score and all will be storing in the cache. So at very high level, if I want to say for example, I am talking to you, you are remembering the context, right? The same thing we are doing. But the problem with existing system that is KV cache is that it's try to pre-allocate a big chunk of memory from the beforehand because it doesn't know how much memory it will require. So if you utilize the full memory, then it's fine, well, good. But what if I don't use the full memory? So what it will do, if I don't use the full memory, it will not try to reallocate the unused type of memory. So the basic problem that we have seen with the KV cache is the memory fragmentation. It's not able to handle the external memory fragmentation well. And this is the main part that vLLM tries to address. The secret sauce of vLLM is page attention, apart along with the other advantage that I have talked about. So this page attention is a similar concept of paging in OS. So what it does, it breaks the large KV cache into sequence or smaller number of pages. So what the advantage of this? It's not trying to allocate a big chunk of memory beforehand. It's trying to allocate the memory on demand. If you look at this diagram, so we have given a prompt like Alan Turing is a computer scientist. So the moment we are generating the next token, say for example, renown, so it will try to generate the or allocate the memory on demand. And the architecture is something like that. In the logical view, the tokens are next to each other, but in the physical block, the tokens need not to be next to each other, and the mapping will be done by the block table. And due to this fashion, I don't need to allocate a big or continuous chunk of the memory. And this is how I am addressing the external memory fragmentation. So we have tried to do some kind of experiments, like we have tried to give 100 prompts and the same operation same prompt, same questions we try to pass using vLLM as an inference engine, and we have also tried to use uh, Hugging Face transformer. So the result that we have seen, like with vLLM, we have noticed 2.7x of improvement in terms of throughput. So the moment I am increasing my throughput, that means I am improving my uh, generate the speed of generating tokens per second. So the moment I'm improving my throughput, I am somehow optimizing the energy. I'm not spending that much time. Okay. So now, like, why, so we talk about like how to optimize the GPU. So now, like, is there any process available with which we can optimize our model? We don't want to use, say for example, small language model. We want to use LLM, but we are trying to cut down the size. But there is no free lunch, right? So there is always a trade-off. So when we are trying to optimize a model, what are the factors we need to take in under consideration? So we took this slide from NVIDIA Summit. So this has nicely shown like the in last few years the pace in which the models are growing. The red line is showing how the model is growing, and the yellow line shows the GPU speed, how we are evolving the GPU. So there is a huge gap between the model size or the number of parameters the current model has and the GPU speed. So to breach this gap, we need an efficient algorithm. So what this efficient algorithm can do, so this can help us to reduce the model size a little bit without much affecting the accuracy. And the second thing, what we can do, we can improve our inference. So in vLLM open source repo, we have also one more technique or one more API called LLM Compressor. So the advantage of LLM Compressor is like we are trying to quantize a model, but without affecting the accuracy much. And it supports like wait only quantization or activation only quantization, like depends on your use case, you can choose it. It also supports sparsity, like you can make your model fit and lean, like removing the unwanted weights. So if we can do this kind of tweaks, so we are eventually going towards less energy consumption. And like if we can cut down the, so we are not only focusing on energy consumption, we are reducing the compute. So when we are reducing the compute, we are reducing the cost. So once I am reducing the cost, I am reducing the energy, so I am like going towards sustainable AI, and we can democratize the AI more speed in a more efficient way. So this is an example like how we can say if we can cut down the size of the model without affecting the accuracy, or if we can quantize the model in a smart way, we can significantly reduce the GPU consumption. So we took a model called Llama 4 Scout, which consists of 109 billion parameters. So this is very rough calculation. If you have the number of parameters multiplied by 2, gives you the how much GPU you need. So say for example, by default all the models comes with BF16. So my model size, that is 109 billion parameter multiplied by 2, we need 220 gigs of GPU to run this model. So we need roughly 3 GPU. But if I can cut down the model size, say for example, instead of BF16, if I can reduce the BF16 to floating point 8 or int 8, so we can see from 16 bit we can reduce to come to 8 bit. Okay, 8 bit. So we can see significant amount of memory reduction. If you see here, so by running if I try to run the default model BF16, I need 220 gig of GPU. But if I try to run int 8 or f8 fp8 model, we just need half of them. So directly we can reduce the 50% of the GPU. So these are the types of the quantization scheme. But before we quantize any kind of model, we need to be very much sure like what we are doing. So what's my use case? Is my use case is compute based or memory compute bound or memory bound? If I am trying to develop a Q&A bot or chat bot where a latency plays a vital role, a user cannot like put a query and wait for 5 minutes, right? So here we are not doing the compute bound operation. What we are doing memory bound operation, because we will be loading the model to fetch the weights and do the matrix multiplication, and then we'll get the results. So say for example, if my goal is use case is to improve latency and my hardware is Hooper or Ampere, so then I have only these two scheme, int W8 and A16. That means I can quantize the weight, I cannot much quantize the activations. And for throughput, like we can use the similar approach. So now let's try to quantize a model. So here we are just loading the model and preparing our data set. So in LLM compressor, the beauty of it is that you can write your own recipe, what you want to do. So here I have used two algorithms, smooth quant and GPTQ modifier. We are not touching the LM head, and we are using the scheme W8A8. That means we'll be quantizing the weight to 8-bit and activation to 8-bit. And then we are calling the one shot API and passing all the model details, recipe details, uh, and the calibration data set. So, so why do we need calibration data set? Because when we are playing with activation, we need to pass a data set. Using that data set, we will do the calibration and we'll see if I can quantize this activation or not. And as an output, we will get a compressed tensor format that is easily easily can be run to any platform. So we have done the quantization. So now what about the accuracy, right? That matters a lot. If the accuracy, if I am going to compromise with the accuracy, then I can go ahead with the small language model maybe. So we try to run a benchmarking. So we use a data set called GSM8K. And if you see here, so in strict match, uh, in terms of the original model is in yellow, giving 68% of accuracy, and my quantized model is giving approximately 67. And for flexible match, it's giving even better result. So this is the detail of the graph. This is the full ecosystem. We have our model here, we have our data set to calibrate it, we can use the LLM compressor to quantize it, and the output compressed tensor can be used by vLLM to load the model, and you can use any tool calling any application to connect with the vLLM. So this is a complete ecosystem. So we have a demo here. So let me just try to run this. So what we have tried to do here, so we took a model, uh, let's see which model we have. So we took Qwen BF16 model that consists of 110 billion parameter. So according to my slide, 110 billion parameter BF16, that means we need to multiply it by 2. That means we need 220 gig of GPU. But if you see here, I have approximately 160 gig of GPU. So I cannot run this model, right? So let's see if I can run this model. So here I am trying to run the model. So tensor parallelism 2, that means we are trying to use 2 GPU. So I will just take a pause here. So this is so we are taking 110 billion parameter model. We are trying to allocate 2 GPU and we are trying to run the model. Let's see if we can run the model. So if you see here, it has failed. We are not able to run the model. So because of the memory constraint. So now what we will do, we'll try to quantize the, like we already have the quantized model. We'll try to run the quantized model. So the original model size was approximately 200 plus. If you see the size of this model, it has been reduced to half of it. That means approximately 106 gig. So we are using WA8 and A8 scheme. That means we have quantized the weight to 8-bit and activation to 8-bit. Now let's see if we can run this model. So it's trying to load the weights and everything. If you see here, we are able to run the same model. So the gist of it, so the same model we can run on comparatively less hardware. And when we run on less hardware, we are trying to use the less number of GPU. And as a result, we can, like, even when we are scaling up the AI or when we are trying to scale up the AI, so there will be like lot of energy consumption. So how we can minimize it, right? So I will pass this the control to Anindita, so she will like brief you more about it.
Thanks, Abhijit. And thank you for patiently listening to the maths heavy part of stuff I'll be talking about on a more lighter note. So before I dig deep into green AI, so let's talk about what does this CO2 footprint, or we hear a lot carbon emissions. So what does this really mean? So I'm sure some of you must have traveled by flight today. So while booking the ticket, did you notice that some sentence was written 160 kg of CO2 emissions? So do you know what does that mean and why it is relevant to what we are trying to showcase here? So what is the meaning of it is like whenever we use any kind of electricity or we travel by flight, even buy a new gadget, unknowingly we release carbon dioxide and many other greenhouse gases into the atmosphere. So we know from our childhood concepts that they trap heat and therefore that leads to global warming. So why is it even relevant? So let's see how we connect this to green AI and how it is a big problem in today's time and how it can lead to better use of democratic AI. Okay. So the problem that we have today is that everybody is using generative AI, but the problem is large language models require a lot of power to run. They are power hungry. Even training a GPT scale model once requires lot of huge tons of CO2 emissions. So it is bad for the planet. Also, it is bad for the business because that leads to a lot of GPU and compute, which makes running business on huge money, which is a problem. Plus, it's a inference, like Abhijit already explained, training is still a one-time activity, but inference happens day-to-day basis. Many people use it for diverse things and it is happening at a global scale. So we have a huge emission problem globally. So what is the possible solution to all these problems? So green AI says that we have to draw a nice optimization between the accuracy of the model as well as the efficiency of the model. It's not that how big your model should be. We should also think that to get that particular accuracy number, what energy consumption goes behind that. So there was this very good research paper by Squats in 2020, which was a breakthrough. and they tried to compare what is red AI versus green AI. So red AI is something like, imagine like a car race. So the researchers, developers, they are crazy behind accuracy. So they want to get good results, good numbers, but they don't think about the compute that goes behind it. And not everybody can afford it today. So, huge companies like Meta, Google, they can still afford it. But what about small scale researchers, academics, startups? What will they do? So that's a blockage to democratic AI. Also, that's not something that is sustainable. And we are already seeing the problems today. Like, there was a recent news that some data center is being set up, and there was some protest that what will be the water consumption to set up that data center. And ultimately it harms us, the planet, and it will also harm us in some way or the other. So what green AI suggested is that while reporting the accuracy numbers, it is also important to report the uh, performance emission that goes behind each accuracy number. So can we achieve, it argues that, is it possible to achieve those accuracy numbers with lesser compute, like what Abhijit explained earlier? So there are several techniques like LLM compressor, vLLM, which drastically reduce these GPU requirements, and like he showed in the graph, we still maintain the similar kind of accuracy. So, to conclude it, why it matters is because naturally any business wants to lower down its costs. So, the lower GPU hours, the lesser the electricity bills. Lower emissions means you have a lesser CO2 footprint, and this is something which is sustainable for uh, us and as well as the next generation. So, okay, so we understood what is the concept, why it is important, but like the golden rule goes, till you don't measure it, we don't know how to improve it practically. So there is a very good open source library called as Code Carbon, and it provides a CLI interface as well. So whatever your computer program has, CPU, GPU, RAM, it converts that to emission in grams. So before talking about how it is computed, it is also important to know that how do we calculate the CO2 footprint of a particular region. So like, for example, in coal heavy regions like India, the electricity is mainly generated depending on fossil fuels like coal. So they are very heavy on CO2 footprint. Per emission, the grams of CO2 released in the atmosphere is pretty high compared to the cleaner regions like France, where the electricity generation is mostly dependent on renewable sources of energy. So their carbon footprint is less. So the same program or same AI application can release different amounts of CO2 depending on where the data center is located. So what is suggested is that the data center should be located in a cleaner grid. So what they do is they just calculate the carbon emission by multiplying the energy in kilowatt per hour into the carbon intensity, and hence they get the results in grams. Is a simplistic overview of what they do, and they further store that results into a CSV file, and you can visualize that on a dashboard. So it's not only using some dummy data, you can actually visualize the carbon emission of your computer program in real time. So it's a simple example of how to use core carbon in Python practically. So you can just pip install it, it's available. And from this code carbon, track emissions can be imported, and you can just use it as a decorator around your function, and you can also put start stop, and the output can be saved to this emission CSV. It can be visualized with carbon board command. And if you don't want to make changes in your code, they also provide you interface to log in directly to their dashboard. So you can visually correlate the output, and accordingly you can start optimizing your AI application. So just summarizing what we talked about, the practical things, the research things. So the papers are cited here. So LLMs, we know, emit lot of CO2, but using sparser model. So what does sparser model means? So if you have some background of LLMs or deep learnings, when all layers of the network are not activated, only the required layers or weights are activated, that means we need to sparse models. So that results in less maths, less GPU, and hence more efficient, sustainable AI. And we understood that inference is dominating most of the market, so we have to think of techniques which reduce this inference using techniques like LLM compressor and vLLM. Okay, so green does not always mean a bad thing. Green can also be designed carefully to use more sustainable use of AI. I'll just like to conclude by saying that Python is the glue framework for all this, and it ties up all these components like vLLM, LLM compressor, and code carbon. And sustainable interference is not something that is just a hypothetical thing. It's an ongoing work, and the tools to achieve it are already here. So thank you so much, and please stay connected. Thank you.